Hello and welcome back to Calculus 3, section 12.2 on functions of several variables, graphs, domain, and level curves. Before we jump into Calculus 3 and new stuff, I'm going to briefly go into our 2D realm, also known as R2. And I will say that this R2 is actually real axis R crossed with another real axis R. So one of these axes R is x-axis, and that's going to be from negative infinity to positive infinity. The other one is y-axis, also from negative infinity to positive infinity. Now some functions will chop that up, but the idea is that this creates a coordinate system which you have been using since you started your education in math, which is a 2D coordinate system, and you can find the 2D points in there and draw 2D functions. Now, your x-axis was from negative infinity to positive infinity, and the y-axis from negative infinity to positive infinity. The function was denoted as y equals f of x. It had single x as input, and that input sits in a domain. Domain was the set of all values that you can use to plug into the formula. And then y was the output, which we call the range. And as you can see, each one of these is just a one-dimensional number line. So you have x dimension, y dimension, so two of them makes a 2D space. What we are going to do now is we are going to upgrade this. And I just wanted to make sure that you see that the domain is 1D, right? So domain is one-dimensional, and it can be from negative infinity to positive infinity or less. So now we're going to jump into 3D, which is R cubed. And this one has the good old, we already talked about this, 3D coordinate system. You can have the left hand or the right hand, left hand or the right hand. And this also moves from negative infinity to positive infinity, and then negative infinity to positive infinity, negative infinity to positive infinity. We have octets now. And the most important part over here to understand is now that your domain for functions is going to be two-dimensional. So what we are going to have now is that the function is going to be z equals the function of x and y. So z will be computed. Z is dependent variable, and x and y as independent. So over here I have the input, or known as domain, and in this case that domain is the set of all points in xy plane. So that's that, and it is 2D. That's very important. So your domain is two-dimensional now. So good old story from your previous education, right, on this is now becoming a domain for the new creature, and your z is the output, also known as range. Now if you have range, that range would be set of all, but that range is one-dimensional. So what you actually have is a diagram that you can understand this way. You are going to feed in a variable x and a variable y, and when function acts on those f, x, and y, single z comes out. So your input is two-dimensional. Say you have a point over here, x comma y, and your output is one-dimensional. So this point from here will map to a point on z using f of x, y. So it's the same idea as before. You have input, you have output, which are domain and range. You have a rule or a formula which changes one into another. So pretty much nothing is changing, except now your domain is no longer one-dimensional, your domain is two-dimensional now. So if you remember from your Calculus 1 or Pre-Calculus 1 definition of a function, we are going to write the same definition now in 3D. And it's worth writing both. So I'm going to write now first definition for 2D function. So function is a rule which assigns to each x in the domain a unique y in the range. And notation for that in blue, maybe y equals f of x. So that was definition for 2D. Now we go definition for 3D. Maybe I should be using R2 and R3. So now for 3D version of this, function is a rule which assigns to each point xy in the domain a unique z in the range. And we write that as z equals f of xy. We can generalize this to any amount of variables that you want. Any. You can have 17 variable function. It's fine. So if you take a look at these two definitions, they're identical. The only thing that is different between them is that in the top definition, your input is a x value on x-axis, and on the bottom, it's a whole domain. So now, if we are thinking about this 3D case, and we have some shape, that shape will have the domain so let's pick, let's draw. Does anyone remember what this is? A cone, hat, and a dome. Elliptical paraboloid. Thank you very much. See, you put your thinking hats on and your dome starts working, and then you come up with the elliptical paraboloid. Very good, very good. So now we have elliptical paraboloid. So what is that elliptical paraboloid going to give us in the xy plane as we take the flashlight and shine above it? Well, think about it. Elliptical paraboloid, that's an umbrella. All right? You open the umbrella and you shine the light. What is going to be as a shadow on the floor? a circle or ellipse, depending on, yes, if it's squished or not. So it's going to be some kind of a circle or some kind of ellipse. So whatever it is, it's going to have the domain here. So I'm going to say that this over here is the domain. And domain, as we know, is a set of all input points so that we are able to compute output. So let me, no, I don't want that software. Let me also write an equation. Say that we have z equals 1 over x minus 2y. Is this some kind of a formula that gives us 3D? Yes, it is. We see x, we see y, and we see z. So it must have 3. Now, do we know what this looks like? No. But can we figure out this domain? Yeah, we use the same stuff that we used in pre-calculus. If you have something that has a fraction in it, make sure the denominator is not 0, and we're good to go. So we are going to find all values that make denominator 0, and then kick those values out of all possibilities. So what do I have? I can actually solve this for x equals to y, from where y is equal to x over 2. Now this thing is a line. And what this means, since we know this is equation that covers all the points that we cannot have, because anything from this form will make denominator 0. So now, by knowing this, I can claim that domain is set of all points except those along y equal x over 2. So now you can test this a little bit. Obviously you can't test every single value, but you can test this. You know, you can pick random x, y, and then compute z, and you will have a triplet that you can plot on the 3D coordinate system. So let's say you pick 1, 3. If you pick 1, 3, well, z is negative 1/5 in that case, because x is 1 and y is 3, so that's 1 minus 6, that's negative 5, so it's negative 1/5 as the z coordinate. And you can plot that, right? Then you can go and you can say, okay, how about negative 2 and 4? Well, that's not a problem either. You have negative 2 minus 8, negative 10, so negative 1 over 10. And now, let's say you pick x equals to 3, y equals to 6. I mean, x equals to 6, y equals to 3. X equals to 6, y equals to 3. If you pick this, observe. If x is, yeah.
Are the above points correct then? Yeah. Because 3 doesn't equal 1 over 2.
Why would 3 need to be equal?
3 is supposed to be y, and then that's supposed to be the x value. Doesn't the x value have to be bigger than the y value?
Why? We don't have that requirement. We only have the requirement that x is not a log.
I thought you were testing on the yeah.
Well, now when I try 6 and 3, right, I will get no solution over here. So if I have no solution, that means that this point is not in the domain. So not in the domain.
Is there a special notation for like set of all points? Like
Oh yeah. So now what should be the domain? Domain domain would be, well, we can call it the region R or region D or whatever, region D. Is going to be set of all points xy. Now, some books will use semicolon, some books will be using the big line like this. So whatever they say. So all xy, and then these two dots or the big line is read such that, and then we can say that all points except y equals x over 2. So this would be a notation which shows the domain.
Could you do it in terms of x too? Like x equals to y? If you always want it to be y equals.
Oh yeah, either way. There is no preference other than in our heads. There is no preference x comma, because we write the point x comma y comma z, right? And the alphabet, sure. But yeah, there is no preference in that respect. They are both independent input variables. So that's that. So did all of this stuff, did this stuff. I just want to get some homework exercises. It's taking some time. There we go. So now here are some exercises where it said, okay, so what is the domain? And let's go with problem 2. They give us that the function f of x, y, is given by x squared y minus xy squared. So what type of a function is this eventually? And before?
You're asking what type of shape it makes?
No, not the shape. I'm asking what type of a function, what kind of a function this is. You always dealt only with one variable, now you have two, but it's the same thing. Polynomial looking, yes. So this looks like polynomial. Do we see any trig in it? Do we see any e's? Do we see any ln's or logs? Right? So it's not exponential function, it's not logarithmic, it's not trigonometric, right? Are there any divisions? Are there any square roots or radicals, right? So this is the polynomial-like one. And if you recall, the polynomials have the domain to all real numbers. So in this case, what is the domain of this? All points in R2. This technically means that you can pick any xy combination that you can think of, and you will be able to compute and find the z value. So this is infinite domain. Think of the floor as our xy, right? That's what we said. Think of the floor as our xy